Hello everyone. This video today is a little bit different from what I'm used to uploading. Briefly, the story is that I was reading a book. It's titled Machine Learning with R by Brett Lance, the third edition. And it's a really beautiful book. And I found this algorithm, it's my favorite. And the weird thing is that I did not find any video for this on YouTube. There are no tutorials for this. No one seems to be talking about it, even though it's a very powerful algorithm. It combines the concepts from both linear regression and regression trees or decision trees. So I'm assuming that if you're watching this video, you should be already familiar with both of these machine learning algorithms, linear regression and decision trees. If you are not, then I'll put links below in the description, and I'll pin a comment as well with links to teach you both linear regression and decision trees, because this algorithm today actually combines both of these concepts together into a much more powerful model. So anyways, like I said, this is a model combining both, and to enable more people to learn these things in order to be helpful for anyone, hopefully, I've decided to make this video covering it in a small demonstration. So let's get started. This is called the Cubist model tree. Now, the algorithm itself is called the model tree, and the package is by Cubist in R software. So let's get started now. I've created a factitious model. I've created my own data for this example, okay? And it's about the relationship between drug concentrations for whatever medication, drug concentrations in the blood, compared to the efficacy of that drug. So let's create the data, and we have named it right here, as you can see, data frame, DF. So let's start exploring the data first, just to give you an idea of what we are doing. As you can see here, it's the comparison between concentration and efficacy. Now this is a third random variable. It's all zeros really. And I've added it because this algorithm doesn't seem to work except if we have more than 2 or more variables. So you can really ignore this variable, and let's assume that we have these two variables alone. Actually, we can have many more variables. I'm not going to talk about this right now. I'll address it later in the video. So it's comparing the concentration and efficacy. So let's plot them. So to get an idea of the variables that we are dealing with, let's say plot df at efficacy and df versus the concentration. I just want to color it because I like fancy things. So let's say color is blue 3. Of course, I'm assuming these things really are very easy, so I'm not going to explain them, how to plot things, how to import data. Anyone using these algorithms should be familiar with these things. So anyways, the color and the X label should be blood concentration. Okay, over. So as you can see here, if we just enlarge it a little bit, you can see now that, oh no, this is not so good. Okay, let's change the order actually, because yeah, this is not actually the way I want it to be. Let's put the x-axis. That's the mistake I did. The x-axis should be concentration, the first one, and then the y-axis should be the efficacy. Now let's plot it. Okay, so that's more like it actually. This looks now proper. As you can see here, we are plotting these two variables against each other in a scatter plot. And this is a very useful plot to have an exploration of the relationships between variables before you try to predict them or create a model for them. So as you can see here, we have 3 clusters of data because, like I said, I created this data myself. It's not ideal. It's only for demonstration purposes. So you can see here that when we plot the blood concentration on the x-axis and the efficacy of the drug, df at efficacy, I'm not going to, well, actually, let's change it as well. So let's say y label equals drug efficacy. Okay, so now, okay, so everything looks good. So as you can see, the relationship looks a little bit linear, but it's not perfectly linear. Because as you can see here, if you look now at the lowest part of near both the zeros in the x and the y axis, you can see that the blood concentrations keep increasing for this drug, but the efficacy is not increasing at all. So it's a horizontal relationship. Now, up to a certain point after this range now in this new cluster, the relationship seems to be a little bit linear, because as you can see here, between the range of 20 and 40, let's say this is, milligrams per deciliter, the blood concentration in the unit. So in this range, the efficacy increased as well in the same region, 20 to 40. So it is a little bit linear here. But as we increase more to the 40 to 60 range, something weird happens, and we can see that we've hit a plateau, because as we increase beyond 40, the efficacy no longer increases proportionally with the drug concentration in the blood. So if you follow my mouse right here, so here we have a horizontal, then a linear, then a horizontal relationship again, and we have struck a plateau. So this scatter plot was very, very useful. And if we want to obtain the correlation coefficient between the two, we just do this. So we say COR, correlation, and then just delete the plot, right? So correlation coefficient between the concentration and efficacy. And if you click enter, you will see right here that the the correlation coefficient is 0.87. So that's the Pearson correlation. So there is a relationship, but we can see from the scatter plot that it's not perfectly linear. So if we want to plot it actually, to have an illustration for it, it would look like this. So you can see here that we have a plateau effect. As you can see, it starts. Now this is the illustration of the data that we just displayed in the R software, in RStudio. So here we have first a horizontal relationship. There is no increase. If this is the concentration, this is the efficacy. We saw earlier it didn't increase. After a certain point, it goes up, so it's a really good linear relationship. Up again to a certain point where we strike a threshold, and after that, anything that increases, it results in a plateau. So it's horizontal again, just like in the first stage. So this is called the plateau effect. And this brings us now to a very important question, that if we have such relationships like the plateau effect, or if we have curvilinear relationships where something seems to increase linearly up to a certain point where we have a perfect range and then it starts dropping again, how are we supposed to model such a relationship using machine learning algorithms? And if you are already familiar, like I said, with decision trees and regression trees, you can fix this problem with a certain extent using the regression trees, because of their mechanism. They are very well suited to deal with non-linear relationships. But the good news is that you even have a better algorithm, you even have a better alternative than regression trees, which is the Cubist package, the model trees, which combine both linear regression and decision trees. And this is what we'll be explaining. So this is basically how the Cubist model trees work. If we want to predict Y from X, which is in this case to predict efficacy from concentration, we create early on, we create classification, we create decision trees, we create conditions, and if they are met or not, we progress accordingly So if we meet the first condition or the rules specified, we apply a certain model. If not, we move to a second rule and then a third rule. And of course, this can go up to a very large number. But the point is that in the end, you will reach an end where you cover all alternatives and you will apply different models. Bear with me if this sounds a little bit too confusing. We will explain it very well soon. So let's just follow with the examples. So we had this relationship and now we want to predict it. First, we want to split the data. So let's open the library, of course, library CA tools. Of course, this is going to split our data into training and testing sets. These things are too simple, so I won't explain them. So we use this package to split the data. So we set the seed, let's say, at 0, and then we say split equals sample split, where df split ratio equals 0.8. So we want 80% of the data to be training and 20% of the data to be testing data. Okay, then we move and we say train equals subset and df split equals true, and then we say the same thing for the testing data, but false, and we say here test. Okay, so what we've done right here, we've split the data into training and testing sets in order to apply these models. Now, let's move on to creating a linear regression model first, because we said now we will compare how a linear regression model works and how a model tree compares to it in terms of accuracy. So let's say linear model equals LM. We want to predict efficacy, so we say train efficacy right, and then we say delta, and we want to use the concentration, so we say concentration. Let's check the names of the variables. Okay, so the name is concentration. So we want to predict using the linear model. We want to predict efficacy from concentration. So this is our y variable and this is our x variable, the dependent and the independent variable. Data is equal to train. Okay, and then we say, so we've built now our model, and let's say summary of LM. Now, if you look at the model right here, it has created this linear regression model with the intercept at 7, so at this area right here, and the coefficient or the concentration, the coefficient for the concentration, the beta value, is 0.62. So it's trying its best to achieve a linear relationship. And as you can see right here, if we look at the adjusted R squared, it is 0.77. And the F statistic is significant. Okay, so if we want now to test our variable at the testing data, because we have this model, we want to test it, not on our training data, but on the test split. So let's say ypred, which is efficacy, the predicted y, in our case it's efficacy, ypred of the linear regression model, so y is efficacy, pred because it is our predicted variable, not the true value. The predicted value, not the true value. and LM because we are using the LM linear regression model. To distinguish it now in the future, very soon we'll be comparing it to the model tree. So that's why we are using these words. So predict LM from test. So this function right here predicts efficacy using the linear model and the testing data. Because right here we trained our model, and now we want to test the model on testing data. So let's find first the correlation. So this the ypred variable has been created. Let's find the correlation between ypred, LM, and test efficacy. So we are now comparing the predicted values of efficacy to the true values of efficacy. And the correlation coefficient is 0.78. So let's add it into a comment. Correlation equals 0.87. Okay? And if we want to calculate now the mean absolute error, so let's do this. MAE of LM equals, how do we do it? Yeah, mean absolute. And now we subtract ypred, LM. We subtract from it the test data, the efficacy. Okay? So the mean absolute error, which is a measure of error. Of course, now we should note that the more the correlation between the two values, the better. And in the case of the mean absolute error, it's the opposite. So the lower the mean absolute error, the better. So MAE equals 10.4. Okay, so let's also add it as a note. Equals 10.4. Okay, as you can see right here. So we've added it as a note in order to compare them now soon when we will create our model tree. Now, okay. Okay, this is much neater. So now let's move on to our Cubist model tree. So we have already now created our linear regression model, and as you can imagine, it's very difficult to fit a single linear line using the y equals mx plus b formula, because this creates a linear model. And you cannot really fit a straight line very well through all of these points. You will have a large margin of error, but our model that did its best, and this is the accuracy or the quality of the model that we have achieved, with a mean absolute error of 10 and a correlation of 0.8. So let's now test the Cubist model tree. So let's first import the library. So library Cubist. Of course, if this is your first time using this package, then you should first use install.packages and then use Cubist. So you would run this code and then turn on the package, but of course I've already installed it. So we've imported this library, and then we say model tree, okay, equals Cubist. This is of course just the name that I'm granting it. You can name it anything you want, and the same thing here for this linear model. So Cubist, and then we say train -2 and train at efficacy. Okay, so let me explain this code. Cubist, of course, we are using this package. This is the x variable. So we want to use the variable which is concentration. So if we go back to the df, let's actually turn on df or train. It's really the same thing. So let's view train. So if you go here, as you can see, the first variable is concentration, the second is efficacy. The random, you can really ignore it. So what we want to do here is we want to use the dependent, the independent variables. So here you first determine the independent variables. If you actually press F1 for help, this is how the setup should look like. So you have first the X, then the Y, then the control for to prevent overfitting. I will address this in a little bit. So first you put the independent variables, which are the X variables. In our case, we want to use everything except the efficacy itself, because efficacy is our dependent variable. We want to use the rest, which are concentration and the random variable, but you can really ignore it, but we are using it here just to enable our example. So we say train minus the second column, which is the column of efficacy. So we want to use this and this without the efficacy column. So that's why we have said we want to use train minus 2. This is for training our model. And then our Y variable is train efficacy. Okay, so now we want to control our model tree, because as you should already know from decision trees, they are excellent tools, but one of their limitations is that they are prone to overfitting. They are greedy and they can overfit the data. So you can use a control command, which is control equals Cubist control, and you should say rules equals to, and this will be a little bit confusing for now, so please bear with me. We will come back to it. So in this case you create, just like in decision trees, you determine how many splits do you want, or how many divisions or splits, or how many leaves and so on you want to prevent overfitting, or the max depth. In this case, this is its equivalent in the Cubist model trees. So you determine how many rules do you want. We will come back to it, but let's put the number 3 right here. We will explain why we have put a number 3. Of course, this can be different in different models, in different data, but in our data, the number 3 is very suitable, and we will address why very soon. So our model tree should be ready, and now let's predict. So let's say ypred M3. We want now to test our model on a testing set instead of the training set. Okay, so we say ypred M3, which is our predicted Y value, the efficacy, from the model tree. So we say predict using M3 on the testing data. Okay, so we have now made our prediction. How do we find the accuracy of the model and compare it to the previously created linear regression? We will use the same methods that we already used. So let's just copy and paste our code here to save time. So let's first just make a column here, a row, to avoid confusion. So use pred M3, the ypred M3, to compare it to the efficacy, and the correlation coefficient between the predicted Y values, the predicted efficacy using M3, the model tree, compared to the true values of efficacy in the testing set, is 0.96. So that's a much more powerful correlation, a much more stronger relationship than the one created by the linear regression model. So let's copy it right here as to not forget it. Okay. Okay, and if we want to calculate the mean absolute error, we say MAE of M3 equals mean absolute, the mean of the absolute value, and we subtract this one from the predicted efficacy using the M tree. Okay, so this is the values or the set of values that we have obtained using this function. So we use the model tree on the testing data to predict the efficacy, and we have stored them in this variable. So we are now subtracting this to calculate the mean absolute error. So it's pretty basic, and MAE of M3. So the mean absolute error now is 3.5, and this is really amazing. So MAE equals 3.5. So okay, so as you can see here now, the correlation here was between the predicted values. It was 0.87. In our Cubist model tree, it is 0.96. So it's a good increase. And the mean absolute error in this also linear model, it was 10. But in our new Cubist model tree, it became 3.5. So as you can see, this is a much stronger model. Now up to this point, you may be confused because we don't really understand what's happening behind the screen. And actually, I should have explained this earlier, but let's do it anyways. So let's go back to our PowerPoint slides. So if you look at our relationship here between the concentration and efficacy, it had this shape. The problem is that you cannot fit a single line through all of this data because it will result in inaccuracy. Whether you do it like this or like this or like this, you will misestimate many values on the opposite side. So how do you solve this problem? If you imagine now, if you can fit a linear regression model, we can easily fit 3 lines because these are all linear relationships almost. But the problem is that they shift. So we create rules. So first we assume that they are different data. So we cut off the data right here and we create a rule for it. So anything below this certain value, we will use a certain model for it. And then also we cut off the data right here and we will use another model for this range between this point and this point. We will use a different model. And anything above that, we will use a third model for them. So we can use 3 separate linear regression models according in different thresholds, above or below different thresholds. So, and this is exactly what we do right here. So if we go back to our data and we go back to our plot, as you can see here, anything below this point, about 7 or 10, it is horizontal. In between, it is linear. And anything above that is again linear, but horizontal. It's a horizontal relationship, plateau. So this is what our decision tree does. So we go back here. So if you now predict, actually let's go back here to avoid any confusion. Let's analyze the Cubist model tree itself. So if we want to see what the model tree has, okay, to interpret the model tree, you say summary and M3, the name of our model. So we open the screen and here it is. I've intentionally used a small data set with only 2 variables to avoid confusion, because this would be much more confusing with many variables. Even though it can be done, but it can be more confusing for demonstration purposes and for learning purposes. So here our model tree has been summarized, okay? And you can see that here we are reading the 266 cases because our testing set should be, our training set, excuse me, it is 266. So we train this model using this number of observations or cases. So this is the number right here, and we have 3 attributes from undefined data. We have created this model already in R. And this is the model summary. The rule 1, so we are now creating thresholds, just like we said here. We are using cutoffs, right? So this is exactly why we determine the number to be 3. So the rule number 1, if, so we have if statements. If the concentration is less than or equal to 7, I'll be ignoring the decimals. So if concentration is less than or equal to 7, then the outcome shall be 0. And this is really what you can observe right here in our data. Anything below this point is equal to 0. So our model judges this, by this number. So on the second rule now, if the first rule was not satisfied, if the first condition was not satisfied, we move on to the second rule. If the concentration is above 7, but below 39, right? So if it is above this area, above this threshold, but below this number, so in this range, and if we go back to our diagram right here, you can see if it is above this point, but below this point, we have created a new rule, which is rule number 2. So then the outcome is a linear regression model. So a linear regression where the intercept is 20 and the beta value, the beta coefficient is 0.33 times the concentration. So it takes the form of y equals mx plus b, where y is the efficacy, b is the intercept, which is 20, and m is 0.33, and the x is concentration. Now the third and final rule is that if it's neither 1 or 2, if it is above 7 and also above 39, so if concentration is greater than 39, then the outcome is 60. So because it's a horizontal relationship. So we have created 3 separate linear models using this Cubist algorithm. And this is actually what happens right here. So predict y using x to predict efficacy from the drug concentration. Did we meet the first condition? In our case, the condition was to be less than 7 point something, less than 7. So if we meet this condition, yes, then we will apply the first model, which was y equals, what was the formula? Yeah, the outcome is 0. Okay, so this is just an example, ignore these numbers. It's actually 0 plus zeros, it's all 0. Okay, if we haven't met this condition, so if it's above 7, then we go to meet the next condition, which is being above 7 and below 39. So do we meet this? And this is this cluster, this applies to this cluster of data. So if we meet this condition, yes, then we apply the second model, which is y equals 20 plus 33 times concentration. Ignore this number, it's just an example. So we apply this model, which was determined right here. Okay, if not, if the second condition is not met, then we say no, again no, and we ask, do we meet the third condition, which is being above 39? And because it's now excluding all the possibilities, this is the final possibility, there is no alternative, yes, and we apply the third model, which is 0 times x plus 60. So y equals 60, which is the value right here that we have found. So let's go back to our model tree. Yeah, so you can see right here that we create 3 separate linear regression models, 1, 2, and 3, according to the different thresholds or conditions that we meet. So you can see that this model fits this area of the graph very well. this model, which is the second condition, the second rule, fits this area or this portion of the graph very well. And finally, this third model, which is a horizontal one again, fits this portion of the graph very, very well. So this is what the Cubist model tree does, actually. And you can see this again if we go here. So this is the Cubist model tree. It's just like a regular decision tree. It starts this way at the beginning with the regular thresholds and conditions, but it splits and ends with linear regression models. In the case of regression trees, you end with numbers, with estimations of numbers, of the average, of the mean. While in this case, instead of ending in the average, we end with linear regression models. So let's close this. So like I said, I'm going to explain why we have used the control to be rules 3. Because if we do not specify this actually, and if we leave it to default, okay, if we apply this now without any control, what will happen is that more models can be created. So M3 equals so on. And if we use now M3 summary, now I have removed the limitation. In this case, it did not happen, but more rules can apply. So if you did not set a control variable to control the growth of your tree, it can result in overfitting, and it can result in more rules than you want. So according to the scatter plot that I can see, and because I created this data myself, we can already see that we only have 3 stages of the data. Okay, so we only have the first phase, the second phase, and the third phase. Therefore, I decided that it was ideal to use 3 rules only. And this is why we said we have used this code to say control, Cubist control equals to 3 rules. Now, of course, if you're using or you're analyzing unseen data, you would want to change the number of rules that you want and cross-validate them using the training set and the testing split to see which one achieves the best accuracy and the lowest mean absolute error and the best correlation and so on. So this is just like any really other algorithm. You keep changing the variables, you validate it in the testing set to see which achieves the greatest accuracy and the greatest predictive power. So yeah, this was the Cubist model and decision trees. I hope that you found this helpful. I mean, this is a really, really amazing algorithm. It's perfectly suitable for finding or analyzing relationships that have a curvilinear relationship, right? So you can never really fit a single line through this relationship, even though it's a clear one, but you know, you cannot use a linear relationship for this. So a Cubist model tree can be really ideal here. Or also, like I said, in the scenario where you have a plateau effect, Cubist model trees can help you achieve much greater accuracy. So I wanted to share this because, like I said, I didn't find any YouTube videos covering this. And I also would like to thank Dr. Brett Lantz for his amazing book, Machine Learning with R. I've really found it insightful, and I mean, this is my favorite algorithm so far out of the many I've seen. So I hope you found this helpful, and thank you for watching.